In the context of stock trading, these technical indicators can also be considered features that are used in data analysis to better understand stock performance. One of the most common methods for predicting market movements involves the use of technical indicators, which are mathematical calculations based on the price, volume, or open interest of a stock. In the world of financial markets, making informed decisions about when to buy or sell stocks is a complex task. So let's start coding.
This code snippet is setting up the environment for a stock forecasting project that involves features engineering. First, it imports necessary libraries. Pandas_datareader is used to fetch financial data, while NumPy and Pandas are essential for data manipulation and analysis. Visualization libraries like Matplotlib and Seaborn are included to create plots and charts for better insights. There are also imports for specific functions from the features_engineering module, which likely contains methods to compute various technical indicators like moving averages, MA7 and MA21, relative strength index, RSI, moving average convergence divergence, MACD, and Bollinger Bands. These indicators will probably be used to engineer features later on. The imports for web scraping and sentiment analysis include Beautiful Soup for parsing HTML data, requests for making HTTP requests, and Sentiment Intensity Analyzer from the NLTK library to analyze the sentiment of news headlines related to Tesla. Warnings are suppressed to keep the output clean, and the default DPI for Matplotlib figures is set to 227, which likely optimizes the visual display for the developer's screen. Overall, this code snippet lays the groundwork for fetching data and performing analysis needed for stock forecasting, particularly focused on Tesla and its associated headlines. This code snippet is using the Pandas_datareader library to fetch historical stock data for Tesla, identified by the ticker symbol Tesla, from Yahoo Finance. The get_data_Yahoo function takes two arguments, the stock ticker and the starting date for the data retrieval. Here, it's set to start collecting data from 1980 onward. This means you'll get daily stock prices, volume, and other financial metrics for Tesla from that date until the most recent data available. Once the data is retrieved, it is then saved to a CSV file named raw_stocks.csv in the data directory. This is helpful for later analysis or processing, allowing you to work with the data offline or in other programs that can read CSV files. The code snippet tsla_df.head is used to display the first few rows of a data frame named tsla_df, which likely contains historical stock data for Tesla. This function is particularly useful for quickly inspecting the structure and contents of the data frame, allowing users to verify that the data has been loaded correctly and to understand its format. The output shows a table with several columns, high, low, open, close, volume, and adjective close, indexed by date. Each row represents a specific date, providing key metrics for Tesla's stock on that day. The high column indicates the highest price reached during the trading day, while the low column shows the lowest price. The open column reflects the price at which the stock opened for trading, and the close column indicates the price at which it closed. The volume column represents the number of shares traded, and adjective close provides the adjusted closing price, which accounts for dividends and stock splits, offering a more accurate reflection of the stock's value over time. For instance, on June 29, 2010, Tesla stock had a high of $25 and a low of $17.54, opening at $19 and closing at $23.89, with a trading volume of 1,876,630 shares. This data is crucial for stock forecasting models as it provides historical context and trends that can be analyzed to predict future stock performance. The ability to view this data in a structured format helps analysts and data scientists to identify patterns and make informed decisions based on historical performance. The code snippet Tesla_df.describe is used to generate descriptive statistics for a data frame named Tesla_df, which likely contains historical stock data for Tesla. This method provides a summary of the central tendency, dispersion, and shape of the dataset's distribution, excluding known values. The output includes several key statistical measures for each numerical column in the data frame, such as high, low, open, close, volume, and adjusted close. The output reveals that there are 2,355 entries in the dataset for each of the columns. For the high price, the mean is approximately 183.33, with a standard deviation of about 114.76, indicating a significant variation in daily high prices. The minimum high price recorded is 16.63, while the maximum is 389.61, suggesting considerable fluctuations in Tesla's stock price over the observed period. Similar statistics are provided for the low, open, close, and volume columns, with the close price averaging around 180.21 and a maximum of 385.00. The volume column shows an average trading volume of about 5.58 million shares, with a maximum volume of over 505.99 million shares, indicating days of high trading activity. The adjusted close price, which accounts for dividends and stock splits, has a mean of 180.21 and a maximum of 385.00, reflecting the adjusted value of the stock over time. The quartiles 25%, 50%, and 75% for each column provide insights into the distribution of the data, helping to identify trends and potential outliers. Overall, this descriptive analysis is crucial for understanding the historical performance of Tesla stock, which can inform feature engineering for stock forecasting models. The code snippet checks for missing data in a data frame named Tesla_DF, which is likely part of a project focused on feature engineering for stock forecasting models. It uses the ISNA method to identify any missing values in the data frame. The sum function is applied twice, first to count the number of missing values for each column and then to sum these counts across all columns. If the total count of missing values is 0, the code prints no missing data. Otherwise, it outputs the count of missing values for each column. The output, no missing data, indicates that there are no missing values in the Tesla_DF data frame. This is a crucial aspect of data preparation, as missing data can lead to inaccurate model predictions and analyses. By confirming the absence of missing values, the code ensures that the dataset is complete and ready for further processing, which is essential for building reliable stock forecasting models. This step helps maintain data integrity and supports the overall goal of the project. This part of the code is handling the loading and preprocessing of stock data. It begins by listing all the files in the data raw_stocks directory and initializes an empty dictionary called stocks to store the data for each stock. For each file in the list, it extracts the stock name by converting the file name to lowercase and removing the file extension. It then reads the CSV file into a data frame using pandas and stores it in the stocks dictionary. Next, several features are calculated and added to each stocks data frame. 1. Return. This feature calculates the daily return by taking the closing price divided by the opening price, subtracting 1 from it, and rounding it to 3 decimal places. 2. Change. It computes the daily change in price, which is the difference between the current day's closing price and the previous day's closing price. Any NaN values resulting from this operation are filled with 0. 3. Date. Here, the date column is converted to a pandas datetime object for proper chronological handling and is set as the index of the data frame, which helps in time series analysis later. 4. Volatility. This is calculated using the exponentially weighted moving standard deviation of the closing prices over a window of 21 days, which provides an indication of price stability. 5. Moving averages. It calculates 2 moving averages, one for 7 days, MA7, and another for 21 days, MA21, using separate functions for each. 6. Momentum. A momentum indicator is computed based on the closing prices over a period of 3 days. 7. RSI, Relative Strength Index. This feature assesses the speed and change of price movements, providing insight into overbought or oversold conditions. 8. MACD, Moving Average Convergence Divergence. This calculates both the MACD line and a signal line using another custom function. 9. Bollinger Bands. These include calculations for the upper and lower bands based on the stock's price data, again using a dedicated function. After all the features are created, any rows with NaN values are dropped to clean the data. Finally, the updated data frame for each stock is saved as a new CSV file in the data stocks directory. The last line shows a preview of the data for Tesla, TSLA, by calling the head method, which displays the first few rows of the data frame. This snippet is designed to scrape headlines and dates related to Tesla from a NASDAQ news page. It initializes 2 empty lists, headlines_list and dates_list, which will store the extracted headlines and their corresponding dates. The loop runs from 1 to 119, meaning it will make requests to the news page for each of these pages, assuming each page has relevant content. Inside the loop, the get_Tesla_headlines function is called with a formatted URL that includes the current page number. This function presumably retrieves headlines and their associated dates. Once the data is fetched, the headlines are appended to the headlines_list and the dates are appended to the dates_list. To prevent overwhelming the server with requests, there's a 1-second delay between each iteration, thanks to time.sleep1. This helps to ensure that the scraper behaves respectfully towards the source website and reduces the likelihood of getting blocked. This line is creating a pandas data frame called Tesla_headlines. It consists of 2 columns, title and a date. The title column is populated using a list comprehension that flattens a list called headlines_list. This means it takes every sublist within headlines_list and extracts each headline, generating a single list of headlines for the data frame. For the date column, we're using a similar technique. It iterates through dates_list, but only grabs the first 10 entries from each sublist, which seems to suggest that each sublist might contain dates corresponding to the headlines. This way, both columns align correctly in terms of corresponding headlines and their respective dates. Overall, you've efficiently combined information from 2 separate lists into a structured format that's easy to work with for further analysis or operations related to stock forecasting. This line of code initializes an instance of the Sentiment Intensity Analyzer class, which is part of the VADA, Valence-Aware Dictionary and Sentiment Reasoner sentiment analysis tool. It's designed to perform sentiment analysis on text data, where it can assess the sentiment of a piece of text and provide scores that indicate whether the sentiment is positive, negative, or neutral. By creating an instance called SID, you can then use this object to analyze various text inputs, extracting sentiment scores that can be useful for understanding market sentiment and potentially improving stock forecasting models. This snippet is processing a data frame called Tesla_headlines, which presumably contains news headlines about Tesla. The first line applies sentiment analysis to the title column in this data frame. It uses a function SID.polarity_scores x compound to determine the sentiment score for each headline. Here, SID is likely an instance of a sentiment analysis tool, such as those from the Natural Language Toolkit (NLTK). The compound score gives a single value that summarizes the overall sentiment of the headline, ranging from very negative to very positive. This score is then added to a new column called a sentiment. Next, the code converts the date column to a datetime format. This is important for any time series analysis you might want to perform on the data later because it ensures that the dates are in a standard format that pandas can work with effectively. Finally, the processed data frame is saved to a CSV file named Tesla_headlines.csv in the data directory. This is useful for preserving the results of the sentiment analysis and the formatted dates for future use, like further analysis or model training. The code snippet Tesla_headlines.head is used to display the first few rows of a data frame named Tesla_headlines. This data frame likely contains news headlines related to Tesla, along with associated metadata such as the date of the headline and a sentiment score. The output shows 5 entries, each representing a different headline. The first column, title, contains the text of the headlines. For instance, the first headline discusses Tesla's use of individual driver data for insurance purposes, while the subsequent headlines reference safety agency citations related to Tesla's autopilot system. The date column indicates when each headline was published, with dates ranging from September 4 to September 5, 2019. This temporal aspect is crucial for analyzing trends over time, especially in the context of stock forecasting. The sentiment column provides a numerical score that reflects the sentiment of each headline. These scores can range from negative to positive, indicating the overall tone of the news. A score of 0.0000 suggests a neutral sentiment, while negative values, such as -0.3818 and -0.6597, indicate a negative sentiment associated with the headlines. This sentiment analysis is essential for understanding how news can impact stock prices, as negative headlines may correlate with declines in stock value, while positive headlines could suggest potential increases. Overall, this snippet and its output are integral to the project focused on feature engineering for stock forecasting models, as they provide a structured way to analyze the impact of news sentiment on Tesla stock performance. By examining these headlines and their sentiments, one can derive insights that may inform trading strategies or predictive models.